I'm Alison Lennon from UNSW Sydney, and the title of my talk today is Terawatt PV and the Aluminium Challenge. I'd like to start by acknowledging my co-authors Marina Lunardi, Brett Hallam and Pablo Diaz, all from UNSW Sydney. When people think about the challenges of Terawatt PV, they often think about material sustainability, and in particular the resourcing of materials like indium or silver, which may be limited in their reserves. But we also need to think about the materials that are going to be needed in large quantities, materials like aluminium, steel and concrete. And we need to think about the global warming potential of producing the materials in the quantity that will be required. So today I'm going to talk about aluminium. Now aluminium is used for the frames of PV modules, it's used in the mountings, especially for rooftop modules, and it's used in inverter casings. And it's used because it's light, low cost, and it's resistant to corrosion. Now in my presentation today, I'll start by looking at the extent of emissions reduction required, and then we'll move on and look at the broad electrification scenario of the ITRPV. This is one of the technology mitigation scenarios, which is most ambitious for the amount of PV required. We'll move on and look at quantifying that aluminium demand and the global warming potential of producing the aluminium required. I'll then move on and talk about strategies for addressing the global warming potential and finish with some conclusions. This is a graphic from Climate Action Tracker that shows the global greenhouse gas emissions leading out to 2100. Now, under current policies, this is the blue area here, we can expect temperature increases of 2.7 to 3.1 degrees C. If we've got any chance of limiting temperature increases to less than 2 degrees, we're going to very rapidly need to reduce our emissions to close to net zero by 2050. Now this has inspired a number of technology mitigation scenarios. One of the scenarios which is most ambitious for the role of PV is the ITRPV's broad electrification scenario. Now in this scenario, it assumes decarbonisation of energy, transport and industry. And it forecasts that by 2050, we're going to need installed PV capacities of more than 60 terawatts and be adding additional capacity of 4.5 terawatts each year. Now this represents a very large increase in the manufacturing capacity from around 350 gigawatt peaks to 4.5 terawatt peak in less than 30 years. And the question this raises is, what does this mean for material sustainability? Now in general, low carbon technologies are more mineral intensive than fossil fuels. Now this inspired the World Bank back in 2020 to look at the demand risk for the materials required for clean energy technologies. Now they assumed the earlier IEA 2 degree scenario, which forecast only 4 terawatts of PV by 2050, and for the crystalline silicon share to reduce to 50% of that PV share by 2050. Now they used a construct called demand risk matrices to visualize that demand risk. The x-axis is how cross-cutting the metal is, and you can see out on the x-axis right on the right is copper, which was the most cross-cutting of all the materials they looked at. So copper is used for wind turbines, it's used for PV, it's used for transmission lines, it's used for lithium-ion batteries. And all the other materials were scaled according to copper. The y-axis is the extent to which production must scale to meet demand. And you see right at the top we have graphite, which is used for lithium-ion batteries. We also have steel, but the World Bank didn't analyse steel because it's multi-element alloy and it's difficult to analyse. But if we look here, we also have aluminium. It's both cross-cutting and its scale by which it needs to be produced is quite large. But the other worrying thing about aluminium is it has a large global warming potential, and that's shown by the size of the point. Now, they estimated the aluminium demand for the clean energy technologies was 103 megatons, and 87% of that was due to PV. The global warming potential of the aluminium production was 840 megatons, and this was because a lot of primary production of aluminium was required as there simply isn't enough secondary aluminium available to produce that demand. So the question we asked is, what is the aluminium demand for the ITRPV's broad electrification scenario? Now in this scenario, it predicts 60 terawatts of installed PV as compared to the just 4 terawatts by 2050 that was assumed by the World Bank analysis. In our analysis, we calculated the aluminium demand required for the mountings, frames, cells and inverters. Now we assumed that crystalline silicon PV remains the dominant technology out to 2050 and that aluminium was only required for the rooftop modules where the lightweight was critical. So for utility scale, the assumption was that steel would continue to be used for mountings. We then used manufacturing data for the amount of aluminium required in the frames and the mountings, and the ITRPV analysis for improvements in module efficiency, changes in module size, and trends like the introduction of frameless modules. Now the analysis here is showed with a breakdown of the aluminium demand for the module frames, the mountings, and the inverters. Now the cell aluminium is insignificant compared to the aluminium used for the other sources. And we were able to estimate that the cumulative aluminium demand to achieve the broad electrification scenario of the ITRPV analysis was 486 megatons of aluminium. Now that's to be compared to the 103 megatons that the World Bank estimated in 2020 for all clean energy technologies combined. Now the peak demand was in 2050 when PV manufacturing needed to scale up to 4 to 5 terawatts per year. And to put that aluminium demand in perspective, the global aluminium production in 2020 was 65 megatons. Now, as the World Bank analysis showed, all that aluminium can't be produced through recycling. Primary aluminium production is required. Now, the primary aluminium production process involves the mining of bauxite ore, refining of that ore to alumina, and then the smelting of the alumina into aluminium. This is an incredibly energy-intensive process. And the emissions intensity of that process is largely driven by the smelting process, which requires a large amount of electricity. Now in 2020, the International Aluminium Institute looked at the emissions intensity as a function of the type of electricity grid that was used to provide the electricity for the smelting. Now the world average at that stage, or in 2018, was around 16 tonnes of CO2 equivalent per tonne of aluminium. But it increased to over 20 if the electricity was provided by a coal-fired electricity grid. But if the electricity is provided by low carbon power, then the emissions intensity can be reduced to 5 to 6 tonnes of CO2 equivalent per tonne of aluminium. Now, since 2000, most aluminium is produced in China due to cheaper electricity. And in 2020, 37 megatons of the total global aluminium production of 65 megatons was produced in China. As I mentioned before, aluminium is highly recyclable, and 75% of all the aluminium produced is still in use today. Secondary aluminium uses about 5% of the energy and generates 3 to 5% of the emissions of primary aluminium. But the amount of the resource depends on the available scrap. Now in 2020, Li et al. Published an analysis looking at the aluminium pool in China. They used a combination of historical data, knowledge of the in-product aluminium, recycling and collection rates to estimate or forecast the pool of secondary aluminium in China. Now you can see here that it actually increases out to 2040 but then stabilizes out to 2080. We estimated the global warming potential of the aluminium demand for the broad electrification scenario. We made a number of key assumptions. First, that both the aluminium and PV modules are manufactured in China, and that 33% of the recycled aluminium pool that was forecast by Li et al. Could actually be used for the PV module manufacturing. We assumed that the recycled aluminium content in the frames and mountings and inverter casings was 34% in 2020 and increased to 75% in 2050 due to improvements in the way the secondary aluminium is incorporated into those products. We then looked at a number of different primary emissions intensity scenarios leading out to 2050, and I show these in the graph on the right. Now, I'm not going to go through each of these scenarios and just highlight a couple. Now, the curve in purple here is what we can expect if the emissions intensity remains at 14.5 tonnes of CO2 equivalent per tonne of aluminium. Now, this is a value that was indicative of the emissions intensity in 2020. This is going to result in a cumulative emissions of over 3.5 megatons of CO2 equivalent. On a more optimistic note, if we can rapidly reduce the emissions intensity in China to around 5 tonnes of CO2 equivalent per tonne of aluminium by 2030 through decarbonisation of the electricity grid, and then more slowly reduce the emissions intensity to a value of 1.5 tonnes of CO2 equivalent per tonne of aluminium by 2050 through improvements in the process and direct emissions, then the global warming potential can be limited to just over 1,000. Now, to put this in context, this 1,000 megatons of CO2 equivalent is still larger than the 840 megatons of CO2 equivalent that was predicted by the World Bank for all clean energies leading up to 2050. Now, the other aspect of this analysis is when the peak emissions occur, and I show here in the table when these peak emissions will occur for each of the different scenarios. Now, if we look at the most pessimistic scenario where we have very little achievement in reduction of the emissions intensity up to 2050, you can see that that peak of the emissions will occur around 2050. Now, this is only 10 years out from the 2060 where China is hoping to be net zero emissions. But for the more optimistic scenario, then the peak is actually happening in 2030. Now, to look at this more closely, I'm showing here the annual emissions. Now, for the most pessimistic scenario, you can see how those annual emissions are peaking in that last 5 years. And this is where we're really ramping up to 4 to 5 terawatts of PV per year. You can also see from this how insignificant the emissions are from secondary production. Even though we're trying to incorporate more and more aluminium into the pool, secondary aluminium into the pool, really they make very little contribution to the cumulative warming or cumulative emissions of the aluminium production. Now, on the right, I've broken down the annual emissions into indirect, which is this purple region here, through electricity usage in the primary aluminium production. The green here is now the direct emissions from the primary production, and the yellow is, or the orange, is the secondary production. Now, this is for the most optimistic scenario where we rapidly decarbonise the electricity grid by 2030. Now, first you can note that the peak emissions are now occurring around 2030, and the magnitude of that peak depends on the indirect emissions. So if decarbonisation can be achieved even more rapidly than we modelled, then this peak can be reduced. The other thing to note from this graph here is the magnitude of the emissions that result from the direct processes. And it shows that it's not sufficient to just decarbonise the electricity grid, that there will be improvements required in the aluminium processing to reduce those direct emissions as well. So we're going to move on now and talk about some strategies for reducing the global warming potential of required aluminium. Now, I don't have time to go through all the strategies, so I'll just briefly outline the first three and then try and focus on the last option. So firstly, we can reduce the emissions intensity of the aluminium production. This is probably the most obvious strategy, but I'm not going to talk about that today because it's covered in our paper, which has been accepted for publication in Nature Sustainability. We can adopt frameless modules at a faster rate. Now, in the analysis that we've performed, we followed the rate of introduction of frameless modules that is predicted by the ITRPV report, and then we extrapolate that same rate out to 2050. Now, if frameless modules are adopted at a faster rate, then the amount of aluminium required for the frames can be significantly reduced. The third option is we can use alternative materials for maybe the mountings or the inverters. But when we do this, or if we approach it, we need to make sure that we don't introduce materials that have undesirable properties or result in a similar global warming potential. For example, the replacement of aluminium with steel for rooftop modules may not be advantageous because we increase the weight of the modules. Now, the first option that I want to talk a little bit more today about is local manufacturing. If we manufacture modules in the country in which they are installed, we can access lower emissions aluminium production. For example, in Europe, which has access to hydroelectricity, the average primary aluminium production emissions intensity is much lower than in China. We can also access larger pools of secondary aluminium because we can use the home country or the country of installation's secondary aluminium pool. This means the fraction of aluminium demand that can be met by secondary aluminium is much larger, and the emissions intensity or the global warming potential will be less. We can also reduce emissions due to shipping because the cells are a fraction of module weight and a fraction of the module volume. So, in summary, we need to decarbonise electricity worldwide, decrease direct emissions intensity of primary aluminium, use frame and boss components from the country of installation to access lower emissions aluminium and increase the secondary aluminium pool, and increase collection and recycling or reuse of aluminium worldwide. Now, before I finish up, I just want to come back to the situation in Australia because this conference is located in Australia. Australia has 4 aluminium smelters. One is already powered by hydroelectricity, and I don't show that one because it's in Tasmania. The other 3 are in Gladstone, Tomago and Portland. Now, each of these smelters is located in a renewable energy zone. So for Australia, there is a huge potential to very rapidly reduce its emissions intensity for aluminium, especially the indirect emissions through the use of renewable energy. So in summary, achieving targeted PV installed capacities of more than 60 terawatts by 2050 is going to create a large cumulative demand for aluminium due to its use in frames, mountings and inverters of PV systems. Now, producing all the required aluminium can result in a large global warming potential. And to reduce that global warming potential, we will need to rapidly decarbonise electricity to reduce the indirect emissions, and we will need process improvements to reduce the direct emissions. The global warming potential can also be reduced by reducing aluminium usage per gigawatt of installed PV, providing that suitable alternatives are available, and use of locally manufactured aluminium to access low emissions electricity and increase the available secondary aluminium pool. So thank you very much for your attention, and I'm very happy to take questions.